Hello, everyone, and welcome to this Fujipoly America webinar. My name is Katie, and I will be your Global Spec moderator. Now I would like to introduce today's presenter. With us today, we have Daniel Rosero. Daniel is a Sales and Applications Engineer with Fujipoly America. Daniel, welcome to today's event, and with that, I'd like to pass things over to you to get us started.
Hello, and thank you for joining us today for this webinar where we'll be discussing a brief overview of dispensable thermal interface materials. My name is Daniel Rosero, and I'm the Sales and Applications Engineer here at Fujipoly America. Just to give a brief insight into myself and my role here, I graduated from the New Jersey Institute of Technology with a degree in mechanical engineering, and I've been here now at Fujipoly for 3.5 years, where I primarily provide support for our customers in the East Coast with technical advisement, some testing services, and then of course I also do provide support for our manufacturing processes here in the New Jersey facility. Dispensable materials are available in both thin bondline applications and for gap filler applications. When we talk about these thin bondline applications, we're typically talking about something like a thermal grease. For dispensable gap fillers, then we're looking at dispensable materials that can hold their shape and don't require constant load to keep the TIM in place. This is an important characteristic for gap fillers that should be kept in mind, especially if you're someone who hasn't spent a lot of time with them and more time maybe with like a thermal grease. When greases are applied in applications that require practically no gap, they're typically used under a constant load just to keep everything in place. With a gap filler, it's a fixed gap. The material is expected to stay in place and create a thermal path. So just because they're both dispensable materials doesn't mean you can easily swap them out for one another. And that's something that's really important to keep in mind from a reliability standpoint. As with any thermal interface application, you're going to want to understand whether you're working with an interface that just needs something to break up the contact resistance, or if you actually need to fill in a gap. Many customers expect these materials to either hold their shape if there's a gap, or squeeze down to a bond line that's maybe just a few mils thick. In many cases, it's going to be very difficult to find a material that's going to be able to do that. These materials are really designed with specific viscosity, thixotropic characteristics, and particle sizes they're designed for specific applications. So with any thermal interface application, we suggest identifying and understanding the type of thermal interface you're working with. As mentioned, it's really important to understand whether you're dealing with a gap or whether you just need to break down the contact resistance. So the first type of dispensable TIM application is the dispensable gap filler. Here you got an actual physical or controlled gap with some sort of tolerance. These gaps have to be controlled. In other words, there has to be a spacer or some sort of hard stop in the assembly that's going to help set that gap. In these applications, there typically isn't a lot of clamping force, so any stress that's created is caused by the gap filler as it's being compressed and deformed. The other type is thin bondline applications. With these, typically our goal is to break down the contact resistance. These applications usually have the heat generating component in direct contact with the heatsink, so almost no gap. But because of surface roughness, there'll be a high thermal resistance here. So the thermal interface's job is simply to break down that contact resistance, and it does this by filling in all the microscopic imperfections and the pores that you find in the surface of components in heat sinks. So when we're looking at these two types of materials, in many cases we'll use the thermal conductivity to give us an idea of how well it's going to perform. For gap fillers, it's perfectly fine to use this when comparing performance, since a lot of the thermal resistance is just because of the bulk conductivity of the material. However, for thin bond applications, the conductivity is not quite as helpful, since our goal is not just using a high conductivity material, but to keep the bond line as thin as possible. Of course, reliability is just as important as performance, so mechanical stability is critical. You want to avoid any pump out or flow out of the material from the interface. Most suppliers will typically have some kind of durability data under the heat and humidity for these types of materials. Dispensable gap filler materials generally come in two forms. One is a cure-in-place type, and the other is a non-curing. So in terms of the non-curing material, sometimes it does cause concern as it gives the impression that the material is volatile and can change, but that is just not the case. Non-curing is more of a description telling us that we don't have to go through a curing process. Non-curing materials aren't necessarily volatile. They are stable materials that will go little to no change after being dispensed. Two-part systems are meant to be mixed and cured in place, and the mixing typically happens using a static mixing nozzle. The packaging will be a dual cartridge or some sort of system where the A and B components get thoroughly mixed while being dispensed. One-part materials come in one package. They don't require any mixing, and they're typically packed in cartridges or pails and cans for those higher volume projects. Because two-part materials cure in place, you do have the advantages of a solid elastomer-like connector that essentially cures to the exact gap of the application. The advantage to this is we don't have to worry about reliability like we do with some of the materials that stay in a viscous state. You're essentially getting a lot of the advantages of a pad-type gap filler out of a dispensable TIM. Of course, non-curing types, as the name implies, stay in a viscous state. Since these do not cure, some customers do have concerns about reliability. These types of materials are designed to have higher viscosity and thixotropic characteristics just to ensure that the material does not migrate from the interface. Suppliers often suggest things like a max gap just to reduce the risk of pump out or migration of the material. With all materials, you'll want to review and evaluate the durability and test data that suppliers provide. Regardless of the type of the material, they will require some dispensing equipment that can range from low cost to handheld dispensing guns to much more sophisticated higher cost systems. When it comes to thin bond line TIMs, the options are pretty straightforward. Thermal greases is still one of the main options for dispensable thin bond line TIMs. Because thermal greases are non-curing type, they are non-volatile. In some cases, there are greases that contain solvents that will evaporate. Some greases are highly loaded with particles that can make dispensing difficult and require high pressures. So these solvents will help with the dispensing of the material as well as getting it down to the thin bond lines. Migration of grease is a concern, but lower risk than non-curing viscous TIMs. Greases are typically clamped down under a constant load, and we're also working with those thin bond lines that typically are in the hundreds of microns. So risk of anything flowing out is a bit less, but not completely eliminated. Because we are dealing with a viscous dispensable TIM, we still have to consider packaging options. So like with other dispensable TIMs, there will be some sort of industry standard packaging that suppliers will be offer, but they can't come in higher volume containers such as jars and pails. And again, like other dispensable materials, we will have to look into dispensing equipment. These options are really going to change depending on the manufacturing requirements. If you're dealing with a high volume application versus something that's just building a few hundred units. Some customers have even taken advantage of the low viscosity of the material, and they use like a silk screening or screen printing process just to get those thin bond lines and consistency out of the grease. Reasons for using dispensable thermal interface materials can vary. First is from a manufacturing standpoint, and probably one of the biggest reasons for using them is dispensable materials can easily be integrated into automated manufacturing processes with the use of dispensing equipment and robots. Generally speaking, a system that is used to dispense adhesives or other greases with some slight modifications can be used for dispensable TIMs. Another reason is manpower. Less technicians, less operators will be required. It's also a big plus. Instead of a station filled with several operators applying TIMs on a chip, the automated system can typically apply the exact amount of material and do it very quickly, especially for systems that can vary from tabletop units that require one operator to large systems that apply TIMs across multiple components with no operators. Other reasons that are maybe not as compelling but make some people's job easier is that of administrative document control. In some assemblies, when using thermal pads, you might have different size components that would normally require a part number for each one of those pads, even though it's using the same material and the same thickness. With a dispensable material, typically you're just working with one type of package. You're just going to need one part number. So it's just something that makes things a little bit easier. One of the challenges when selecting and working with any thermal interface material often is managing stress. Specifically, how do you compress the TIM while managing the stress so that it doesn't cause any damage to the PCB, the solder joints, or other components? Most thermal interfaces require some pressure to work or create some kind of stress because of the deformation on the TIM. So with viscous materials like dispensable gap fillers, those concerns are greatly reduced when compared to a gap filler pad, but not completely eliminated. Even though dispensable TIMs are designed to work with thin bond lines and gaps, at a certain point when compressing, a dispensable TIM will result in a dramatic increase in the force. So on the screen is a force and displacement curve for a compression test on the SPG50A and the SPG25B NS. The NS designates that it's a non-silicon material, but other than that, they're both designed to be dispensable gap fillers. Both materials are designed not only to break down contact resistance, but also fill in gaps between a few hundred micron and up to 1 millimeter. These materials are stable and will not flow even when there's little to no pressure. These type of materials are formulated with thermally conductive ceramic fillers, and what that means is that at some point during the compression, these filler particles will begin to compact to where they will align themselves in a way that they will no longer flow. So you'll be approaching like a hard stop of these fillers. So looking at the curve for SPG50A, you can see that we don't see much stress as we compress down from 2 millimeters. The load cell isn't registering much of a force for majority of the test, but we start to see it increase as we approach 0.6 millimeters. And then once we get down to 0.4 millimeters and lower, you can see a dramatic increase in the force. And the same occurs with the SPG25B NS. But little changes in the gap can mean a big change in the force when compressing down to those thin bond lines. Trying to squeeze these materials beyond that will create a lot of stress on the assembly. And this is typically not the compression range we recommend our customers to work in, since this is where you'll start to see PCBs start to bow and some components start to break. On this chart, we can see the results from our original test. But this time, we've introduced two more materials. One is our SG60NS, the other is the SG26NS. Both of these are non-silicon thermal greases designed for thin bond line applications. And right away, you can see that the greases record little to no force, even as we go down below 0.2 millimeters gap. But just like gap fillers, we do see a dramatic increase as those fillers begin to compact. But 300 micron versus 150 is a significant difference in regard to thermal performance. So at this point, maybe you're asking yourself, if I can go down to a thin bond line with less force using a thermal grease, then why don't I use it for all my applications that have a gap? Can one material do it all? And really the short answer is no. As you can see in the bottom left picture, grease materials are going to flow. Unlike gap fillers that will hold their shape, the grease can easily pour right out of the gap. It's going to break the interface and compromise the thermal performance. Greases require thin gaps and constant pressure to keep the material in place. Grease applications would usually have a spring-loaded heatsink or maybe some torque spec when they're assembled. But gap fillers, on the other hand, they're stable without any force applied. In fact, only a small force is required to break up the contact resistance. The small force used to compress the gap fillers is enough to do that. Once it's at the gap, there really is no pressure needed to be applied after that. And again, to go back to emphasize something, we really want you to understand that the thermal interface you're working with, and make sure that you're selecting the appropriate material for that interface. So when talking about the dispensing of these materials, one key topic is of course the container or the packaging solution. Suppliers oftentimes will have a wide variety of different packaging sizes and solutions for their customers, really all depending on the customer's needs, whether it's for testing and evaluations, or of course those larger production runs. In the case of a one-part material, some standard sizes tend to be 30, 50, and 300 cc cartridges. But for a two-part material, you'll likely be dealing with a dual cartridge, and with that, you'll need a static mixer nozzle. That just helps ensure that the two components get mixed properly while they're being dispensed. But as you can see in these images, there's a wide variety of different cartridge sizes, styles, dispensing tips. Many of these have different limitations on pressures, and of course there's a compatibility with nozzle tips, threads. So any little difference can make a large change in the impact on the compatibility with the equipment, or of course the dispensing of the material. So in many cases, we tend to see customers maybe already have like a preference in a cartridge or a volume size, or even of course a brand. So that could always be an option from the supplier, just to make sure that the customer gets what they need. Since we're dealing with dispensable materials, customers will naturally need to acquire dispensing equipment. When it comes to trying to decide on what equipment is right for the job, some factors that will come into play are things such as the number of units to be manufactured, the volume of material per unit, operability of the equipment, and then of course the budget. When dealing with simple, evaluating and testing needs, if you don't have access to a cartridge or syringe with a manual plunger, then a compatible handheld dispensable gun should be able to do the trick. But once you get into production runs that are like, let's say, in the lower to mid range of volume, then you may want to consider tabletop units, since these will be able to provide a bit more control and automation to the process. And then of course, once you hit like those higher volumes, then you have these valve and ram systems, which will be essentially fully automated processes. Finally, when talking about dispensing these materials, you'll want to evaluate the best dispensing pattern for your application. Patterns will often depend on the area that you need to cover, as well as the gap you intend to fill. There's no real specific pattern that's going to work best. There's just some things that you want to keep in mind, such as keeping the pattern simple. Any pattern that introduces air into the TIM will impact the thermal resistance. If it's small, it could be negligible, but in other cases, it could be a bit more of a dramatic impact. The picture on the top right, it's a pattern that we wouldn't recommend, since as the material flows, there's going to be a risk of trapping air in between itself. In terms of like the most simplest shape, we often refer to the Hershey's Kiss pattern. It's just a very simple shot that gets placed in the middle of the component. And if you need to cover a larger area, you could use something like a bead pattern. Finding the right pattern or shape will involve some trial and error. Something that could help is placing a glass plate over the pattern, and that just gives you a better idea to see how the material will flow out. So that is the conclusion of this webinar. Thank you again for joining, and if you have any need for more information or inquiries, please feel free to visit us at fujipoly.com. Thank you.
All right, Daniel, thank you so much for that great presentation. So we do have time for some questions from our audience. For our audience members, if you have a question today, feel free to enter it into the Q&A window and click submit. We'll get through a couple of questions today. If you do not hear your question being answered, do not worry. We will get back to you following today's webinar. All right, so Daniel, I'm going to pass it back over to you to answer a few questions today.
So first question I have here is, what is the minimum gap for these thermal pastes? So the minimum gap or minimum bond line really isn't dependent on the filler particle size, and that can vary between each different material. So for thermal grease or paste, that could be under 25 microns, and then for dispensable dispensable gap filler, you're dealing with larger filler sizes. So here, minimum gaps can be anywhere between 80 to 300 microns. And then next question, my application has a non-silicon requirement. Do you have any dispensable materials for this? So if your application has a gap in it, then we can suggest the SPG dispensable TIMs. They are made of silicon, but they are tested for low outgas, and that's as per the ASTM E595 standard. However, if you have a strict non-silicon requirement, then we do have one option, that's SPG 25B NS. That's a 2.5 watt per meter Kelvin non-silicon gap filler. Again, that's SPG 25B NS. B like boy, N like Nancy, S like Sam. And then if you have no gap, if it's basic metal to metal contact, thermal grease, we do have a couple, I think 2 or 3 different options that are non-silicone as well. Next question is, what is the highest thermal conductivity for these materials? So for thermal greases, we go up to 6 watts per meter Kelvin, and then for the dispensable gap fillers, we go as high as 7 watts per meter Kelvin. All right, next question is, any recommendations on reworking thermal greases? It's been a challenge for us to clean. Yeah, so that's always a common issue with this material. It's going to be a challenge to clean, I guess, regardless. And yeah, it can be quite messy, and if you're not careful, if it gets on the bottom of your palm or on the side of your arm, you could easily start wiping it in other locations. So you just have to make sure you're careful around this material. Our general recommendations are just using alcohol, IPA, and then clean rags, lint-free towels or wipes. You might have to do multiple passes on the surfaces or components, but even then you might not get everything. There might be some leftover residue in between cracks or in tight spots. One possible offering that we have is a newly developed material. I don't believe it's on the website yet, but it's a cleaning putty. So again, after you wipe the material, the grease off, and then you still have some residue remaining, just trying to apply this cleaning putty over that area. It's pretty soft, putty type of material. So you can apply a little bit of pressure, and make sure that you're careful around your components, and then just peel it off, and it should start to remove some of that grease. You might have to do multiple passes even with that. But if you're interested in some more information, please feel free to reach out to us on the website on that product. Next question: are these materials electrically isolating? Yes. So anything that falls within the Sarcon family of materials will be dielectric. I don't have the exact specs in front of me, but reach out to us. We can provide you with the data sheet or catalogs for that information. And then last question: do you have any dispensing equipment manufacturer recommendations? Yes. So while we don't have any specific partnerships with manufacturers or don't have recommendations on specific equipment, we can make general recommendations based on manufacturers that we've worked with to dispense our materials, internally, or that we've seen customers use as well. A couple that come to mind are Nordson and PVA. But again, if you reach out to us, we'll provide you with a few more recommendations on that end. Thank you again for your time. Have a good day.
All right, Daniel, thank you so much for answering a couple of our attendees' questions. So Daniel, thank you so much for a great presentation, and thank you to all of our audience members for taking time to attend our webinar event today. Take care, and we will speak with all of you soon.